working with logarithms. Best day ever. Oh my gosh. Yikes. It's be a long day. Yeah. Basically logarithms, tying in with exponentials is what we've been doing. Loving it. Okay, so a logarithmic function is the inverse of an exponential function. Do you remember how to find inverses? No. Well, if we're going to find the inverse, let's say our exponential function is y equals a to the x power. Inverses, when we're finding them algebraically, we flip-flop the x and y value. So if I was doing the logarithmic, the inverse would be x equals a to the y power. Okay, so when we're solving inverses, we flip-flop it, but then we solve it for the y value. So our y value is in the exponent, so it's kind of weird trying to get y by itself. So to do this, we have to take a logarithm to both sides. So this is what it's actually going to look like. We have log base a of x equals y. Or I can rewrite it the other way. Basically, how I like to remember logarithms is these are exactly the same thing. So when you're just looking at a logarithm, it's kind of weird to be like, what the heck does this actually represent? I like to write it as an exponential so that we were finding the exponent instead. So that's our goal, is to rewrite a logarithm into an exponential expression. Yeah?
Yes.
So I would like to evaluate what is log base 4 of 16. And I can rewrite f of x for y, but I want to rewrite this as an exponential expression. How do I do that? I always start with the base. 4 is my base. And we did this last year when we were in quarantine or whatever. We circle around. We add 4 to the y power, I'm going to say, and then it's back equal to 16. Right, you do the whole looping method to rewrite it into an exponential. And then to evaluate, I just have to figure out 4 to what power 16, and I could think of that easily. Y equals 2. So logarithms are basically a fancy way of finding the exponent. The exponent in this case is 2. That's what satisfies the equation. Good with that. Do the same thing. So log base 5 of 1. How would I rewrite this as an exponential? Flippity-floppity around, yes. So what would it look like? Yeah. Yeah. So here's my exponential. That represents this logarithm. So what exponent do I need it to be to equal 1? Out of what power? Yeah. My exponent is 0. Okay, so this one's weird because it just has a fraction. And that's why I want to do this one. Log base 3 of 1 first. How can I write it as an exponential? Okay. Now I have to figure out what exponent makes it. Yeah, it has to be a negative to basically flip the fraction. And then 3 to the 4th power is 81. So yeah, we can have negatives for our exponent. Okay. This is the general principle of what we're doing like all day long. We can talk about properties, which we kind of went over a few of them already. So if we have log base a of 1, we found that the exponent had to be 0 because there's no other power for it to be equal 1. And we can write because a to the 0 power equals 1. Then we wrote this equation into an exponential. That is what it would look like. We have a second property. If I have log base a of a, I can figure out what this is because I would basically try to find a to what power equals a. We a to the first power, so this logarithm is equal to 1. These ones you can figure out right away just because writing it as an exponential. We have another one. So if you ever see a log base a of a, basically it cancels out. This is just equal to the exponent x. Logarithms are trying to find the exponent, so it's equal to the exponent. I could rewrite it as an exponential. It would be a to the x equals a to the x. And the last one. So this is our one-to-one property. So if we have the same logarithm on both sides of the same base, we could write x equals y. So just like our exponentials, if I have the same base to whatever exponents equal to each other, same thing logarithm, same base, I can set each expression equal to each other. So we can use these lovely properties. So if you don't recognize the property, we can write an equation. So I'm trying to evaluate log base 5 of 1. I could set this equal to x, so that way I could write an exponential. Right, I could rewrite this as 5 to the x powered equals 1. So then the x value of this log base 5 of 1 is 0. Right? Or we could have used the second property or the first property. Either way. I could rewrite this as an exponential again, or I could use a property. What property would this fall under? Yeah. So the second one, because I have the same base and the same number, so this is going to equal 1. Done. This is another inverse one, but if you ever have the same base and same logarithm, they just cancel. So this 8 to the log base 8 goes away.
Wait, so log base 8 all.
The whole thing is in the exponent, yeah. 8 to log base 8 exponent. This is equal to 30. Because 8 as base and log base 8 cancel. Here's the other one. Right. It's the 1-to-1 property, so I just have x squared plus 4 equals 29. It's like solve for x. Yeah. Okay. One more thing we have to start on graphs. Okay. So remember our exponential graphs? They were either like growth or decay. So let's just assume it's growth. So if you remember the property about graphs of inverses, they are reflections across y equals x. So if I reflected it across this diagonal line, my logarithm graph is going to look like this. Okay? So the graph of a logarithm would be this. The main focus is my asymptote is now vertical instead of horizontal. But you'll be given like a logarithm in standard form, so you have log A log base b of x minus h plus k. So if you're given all this nonsense, basically you still want to rewrite it as an exponential because it's easier to graph. But if you look at it in this format, with exponentials our asymptote was the k value, with logarithms our vertical asymptote is the h value. So my asymptote would actually be x equals h in our case, instead of y equals k for exponential. Fun, right? No. Okay, so we're graphing basically the exponential and its inverse, log base 4. So we should be able to see the reflection. This is the last one. Okay. So I would make a table for the first guy. What would you like to put in for alpha? Okay. Now get out. You can plug in 1. You get out 4. -1, or the negative first power would be a 4. Yeah, we've done problems like that, exponential. I have a horizontal asymptote on the x-axis. So this is what the exponential looks like. If you remember the trick with inverses, since I know this is an inverse, technically I could flip-flop my table. So my y values for f of x are now the x values for g of x. And the x values become the y values. If you didn't know this, basically I'd take my logarithm and rewrite it as an exponential. So it'd be 4 to the y power, then equal x. And then you're plugging in values for y instead of x. but it still works the same way. So then my vertical asymptote is the y-axis. So you see that goes reflected across this diagonal. I can hold it up. Logarithm graphs are always confusing, in my opinion. I can never get them right. See? Got done by centering. That's for you. Yeah, so this is the first part we're going to do natural logarithms. Yeah. Bye.
Bye. Bye. Bye.